Okay, I think I'm live. Again, I'm never quite sure exactly to the second when I begin. I hope everybody out there is doing well. I hope that if you did an A-level maths exam today, I think it was today, that went okay. Paper 2 revision tonight, so this is going to be preparing any GCSE students who maybe don't have an exam tomorrow, getting you ready for physics paper 2, which is next week. And of course, also doing stuff from 8 o'clock onwards. So 8 o'clock I'm going to be doing an A-level part of the stream, again just looking over some multiple choice questions and so on. So let's see what I've put a poll in the chat, and at the moment we've got roughly 50-50, we've got about 56% saying people are ready for paper 2. This is now exactly 50-50, we'll see how that develops over the night. But hopefully I can do something to help you prepare. Excuse me, I've just been quite busy playing Lego today, setting up a new office, so I haven't had quite time to have my tea yet. So anyway, the stuff we're going to start with for GCSE, again, these are paper 2 style questions. The first one is about a student taking part in the cycle to school week. We've got this diagram here, so just have a quick read of that. Physics offline? No, I mean, I guess it's, yeah. Do transverse and longitudinal waves behave differently during refraction? Pretty much no. They both have, yeah, I'd say if you look at a transverse wave, which is refracting, so it's bending, then, you know, the way that light behaves is analogous or very similar to the way that, you know, maybe a water wave behaves in a ripple tank. So yeah, I think that they behave in a fairly similar way. Bob Squash, version 2. Yes, so, hi Anissa. Right, let's just get on with the question. So I'm just going to have a quick sip of this and then I'm done for my tea. Right, refueled. Okay, so the first question then. We've got a student here and it shows the 2 routes that they take or they could take to school. We've got the solid line, and again, if there's information here, it's always worth adding that onto your diagram. So this is the route that a car would take, whereas this route down here is the route that a bike would take. So again, have all of these things down here. Anonymous says, what's harder, paper 3 or running 100 kilometres? I would say that I probably did paper 3 when I was younger, when I did A-level physics. Don't really remember it, so it can't be that hard. Whereas actually running 100 kilometres, actually over mountainous terrain, I found incredibly difficult. Especially, and I'm not going to show you my actual feet. I guess I probably could get my foot onto the screen here. But I've basically now pulled off 7 toenails, which are all dead. I've got 2 live toenails, and I've got 1 which is really black, so that's coming off soon. So yeah, I would say running 100 kilometres in the mountains was harder than paper 3. Thank you for that question, Anonymous. Okay, so the student claims that their displacement will be less when they ride their bike compared to when they get a lift. Explain if they're correct. So basically, if we look at the distance travelled, so the distance from here to here to here to here is going to be less than the distance that goes up, around and down. Now you could do that by actually measuring the distance in centimetres, knowing that if this is kind of like a scale diagram, then the longer distance is going to be more centimetres and therefore a bigger distance. But if we think about what displacement means, displacement is very much your A to B, the kind of door-to-door distance in a certain direction. So this length here is going to be S, and that's the distance, which is the displacement. Now, are they correct? Well, basically, the distance travelled by the bike is less, but the displacement is the same, so they are incorrect. And I think it's important to say if they are correct or not, and also explain why that is. And this question then is really about the difference between scalars and vectors. So basically displacement is a vector, so it has magnitude, and it also has a direction. Okay. Now the magnitude of the length in meters from here to here is going to be the same if they go by car or by bike, and obviously it's going to be at the same angle. So yeah. They claim that their displacement will be less. Well, that's not true. The displacement is going to be the same whichever way they go. Okay, so that first question there is really about what's the difference between a scalar quantity and an example of it, and a vector quantity and an example. Of course, scalars only have magnitude or size, vectors have size and direction, and we've got distance as an example of a scalar, displacement as an example of a vector. Okay, how did I get to running 100 kilometres? I don't know, to be honest. I'm doing like a marathon this weekend, which is all off-road, so I'm not necessarily looking forward to that. And then in a couple of months' time, I'm doing a 100-mile, 160-kilometre trail race. So, yeah, I'm not quite sure how that's going to work. Okay, one morning the student wakes up late and needs to cycle as fast as they can to get to school. And here we have a diagram that basically shows the bike and the student represented by this. We've got a force B in this direction, a force A in that direction, and they are going to the right. So, referring to forces A and B in the diagram above, on how they change during their acceleration to their maximum velocity, explain why the student initially accelerates but soon reaches the maximum velocity. So this is kind of like the forces acting on the student at their maximum velocity. Now when they first start, there's going to be a force B to the right. Okay, as they get a bit quicker, the size of force B is going to stay the same, but now the size of force A, I'm going to call it FA and FB, this gets bigger. So basically that's at the start, and then this is during their acceleration until they get to this point over here. So what we can say is as they start pedalling, force B is greater than A, so the resultant force is to the right, so they accelerate. So if we look at these two scenarios, until they get to their maximum velocity, the value of force B is bigger than the value of force A. Okay, as their velocity increases, force A, which is the air resistance or the drag, that's going to increase. And that's because the size of this drag force is going to be related to how quickly they're moving. And you can see that because they're going to the right, the drag force must be force A, which is acting to the left. So the drag force is in the opposite direction to their motion. And of course, if you've got force B, this is basically going to be maybe we could call it thrust maybe. It's kind of the force provided by the pedals and provided by the person riding that bike. So that's the thrust force forward, you've got the drag force back. So as their velocity increases, force A increases, so their acceleration decreases. And again, that's because the resultant force initially, if I draw that here, the initial resultant force is all to the right. As time goes on, the size of that resultant force gets smaller until at this maximum velocity, the resultant force is 0. And of course, we know that the force, or the resultant force, is equal to mass times acceleration. So when there's no resultant force, that means that mass will have 0 acceleration. Okay, and by the way, this is a GCSE part of the stream at the moment. Okay, but obviously good revision, and if you are doing A level, then you should know all of this by now. Basically, force A is then going to be equal in size to force B, but in opposite directions, and that means they travel at a constant terminal velocity, which is their maximum velocity. So all of you out there, you'll probably experience this if you've ridden a bike. You might put the same force into the cranks, and there's a point where you just cannot go any quicker. And the only way to go quicker is either to hit the gym and basically have a bigger force that you can apply, or think about how you can reduce your drag force. Okay, some more questions about running. Anonymous, how did I progress up to running 100 kilometers? Basically, I'm not very good at running. I'm quite heavy. I'm like 94 kilograms at the moment, so I'm not really super light. I guess I just progressed and just did more running, so like running 2 or 3 times a week. And then there's a point where after about 30 or 40 miles, it's just painful, and you just got to deal with like the pain and just keep going. Okay, the student has a cycle computer on their bike. We've got the velocity here, the time in minutes, and it tells them, amongst other data, their velocity and riding time. And basically, this is the information which has now been plotted on the graph down here. So this is a velocity time graph, but be careful that the time here is given in minutes. And if you're going to be doing any calculations, you might need to convert the time from minutes into seconds. But they've given velocity in meters per second. What's the drag force when running? I'd say the main drag force when running is just your air resistance, okay? There's probably going to be some tiny drag force between your feet and the ground, but most of that drag force is due to air resistance. Okay, state the 2 points on figure 12 between which the student stops at traffic lights. So basically, if they're stopping at traffic lights, that means the value of v is going to be 0 meters per second. So this is often what you get. You get a graph like this, and we can see that their velocity increases, gets to a maximum value when they're at this terminal speed or terminal velocity. They then slow down, and between E and F, the value of the velocity is 0. So between E and F is where the velocity is 0. They want to calculate their maximum acceleration during the first 90 seconds. Why should they only do the calculation using data recorded between points A and B rather than A and C? So basically, if we've got 90 seconds, that's going to be equal to 1.5 minutes. So this is 90 seconds here. Now, if you just used their starting velocity and their final velocity and divided that by the time taken, effectively, you're working out the gradient of this line. This line here would be their average acceleration, but we want to calculate their maximum acceleration. Okay, and the maximum acceleration is when the gradient is steepest, and if you look at this section here, the steepest gradient is between A and B. That's when we have maximum acceleration, effectively no drag force, and then as they get faster and faster, the drag force has a bigger effect until the acceleration drops to 0 at this point up here. Okay, after B, their acceleration decreases, and if you use data from A to C, you know, just A equals V minus U over T, that would just give their average acceleration. Okay, how are people doing? We've got 83 votes in now. If you haven't voted in the chat, in the live stream, you can do it. I think at the moment about 63% of people are not ready. They're not feeling confident. They're not ready just yet for paper 2. But if you want to vote, you can easily just do that in the live stream, and there's like a poll at the top. So yeah, we'll see how that develops during the live stream. Hopefully some of the work I'm doing can kind of shift the balance to get more people a little bit ready for it. Okay, state the effect would have a calculated value for maximum acceleration if the student calculated it from A to C rather than just A to B. So the effect would be a lower value than the actual maximum acceleration. We could probably work it out. So for example, we can see here that they accelerate between A and B. They accelerate by 6 meters per second in 30 seconds. So the acceleration from A to B is going to be equal to 6 divided by 30, which is 0.2 meters per second squared. Okay, if we just use the data from A to C, their acceleration would be equal to 8 meters per second minus the initial value of 0 over a time of 90 seconds, and 8 divided by 90 would be equal to 0.089 meters per second squared. Okay, hopefully that helps. Right, how are people doing? The more people are voting, people are feeling slightly more confident the more people vote. Of course, if you are watching this live, you can click the little heart button in the chat, or I don't know what those symbols mean, but I guess YouTube like the analytics of people clicking on things. If you're watching the live stream replay, that obviously you can find on YouTube, you know that if you're watching the replay, make sure that you do like the video, share it with other people in your class. And I will be here for the next week doing live streams in the evenings. How far does the student travel between points C and D? So if you want to know the displacement, that's equal to the area underneath the line on the velocity time graph. I think the hardest thing actually is just identifying the right area. So we're going to look at this area here between C and D. Now luckily that's a lovely kind of rectangle. It's basically equal to the time, which is 1 minute, multiplied by their velocity, which is 8. Okay, so that's 8 meters per second for 60 seconds, which is 480. So they travel 480 meters during that time. When will I be doing OCR A Physics Paper 2? Anonymous, I'll be doing that from sort of 8 o'clock in the stream tonight. Okay, is that a different Anonymous? Okay, right. Next question is number 7. X-rays can be used for medical imaging. Complete the following sentence to explain why they're suitable for medical imaging. So you do need to know, this information, which is basically about electromagnetic waves and some of their uses. So, okay, Evil, not feeling confident in your performance after that live stream. Okay, I would say that that question, the last one, was like a grade 8 or 9. Because it's actually asking questions which even A-level students would find difficult to answer. So I reckon that the stuff about forces is like a kind of definitely a higher tier, more demanding thing. It's not very structured. I reckon the question about the velocity time graph is more like a 7 or 8. Okay, so what I tend to do with these questions is kind of aim at the top end and try and drag everybody up. And if I do these difficult questions here and you kind of follow along, when it comes to doing real past papers, you'll find that actually, or even the real exams, you should find they're a lot easier. Okay, so like train doing really hard problems, and then your GCSEs will be super easy by comparison. Okay, so X-rays are absorbed by bones, but not by soft tissue. So I should have had a Lego figure, but basically the X-rays, they are electromagnetic radiation, and they will penetrate through soft tissue like muscle and blood and things like that, but they're stopped by denser objects, including bones. Now, of course, some of them will go slightly through the bone, so you can actually see inside the bone, so actually maybe work out where it's cracked. Also, in imaging, we tend to use other things like barium and iodine, and these actually stop X-rays. So you can actually inject iodine into the blood or barium into the stomach, and that means you can see where like the blood vessels are. You can see you know, where food is being digested, or maybe where there's some issue in digestion. So you can use other materials to actually identify using an X-ray what's happening in the soft tissue. Okay, name the part of the EM spectrum with the frequency higher than X-rays. It's gamma. All of you should know the song by now, but of course we've got radio, microwaves, ultraviolet, visible, infrared, then we have X-rays, and then we have gamma. Okay, these ones over here, the infrared, X-rays and gamma, these ones are highly ionizing, they carry more energy, and X-rays are basically produced when electrons decelerate, and gamma radiation is emitted when a nucleus basically gets more stable and it emits a little packet of energy. Isn't infrared? Oh yeah, sorry, I should know that. What am I saying? UV over here, infrared over there. Yeah. Yes. Okay, everybody in the chat, because the chat's about 20 seconds behind what I'm saying. Evil, perfectly identified, microwaves, infrared, visible, ultraviolet, and Hasali 19. Yeah, this is GCSE at the moment. But of course, if you're an A-level student ready for the stream at 8 o'clock, if you want to kind of see the next bit of Lego being unleashed, stay tuned. So, the absorption of X-rays can be tested using a plastic polymer that has a specific density. We then calibrate an X-ray machine. All of that stuff is just trying to give you some context. So this stuff here, if you see stuff like this and you just think, what on earth, I've never been taught that, don't worry about it. It's just trying to set the context for this bit of physics. So we've got some information here. Complete table 2 by filling in the missing values. So for this, you had to work out the average. Now, for these bits of data here, these are all pretty similar. So you just add them all up, divide by 3, and you get the mean value. And I've given the value here to 3 significant figures because we've basically got 3 significant figures or in all of our raw data, or 1 decimal point. And that means I've given that to 3 significant figures. Now, what you might not be able to see on the live stream is that this number here was actually 9.5, and therefore it is an anomalous piece of data. If you have anomalous data, often at GCSE it will kind of signpost for you to identify it, but basically you ignore that and don't use that to calculate your mean. So we basically just worked out the mean of 18.1 and 17.9, which you don't even need a calculator for, is just 18.0. Right. Okay, people keep asking, Anonymous, these are great questions. How much running should you do? Just keep running. I basically didn't like running when I was at school. I think all I did was ride my bike. I just hated running, hated cross country. And it's only really when I did stuff with the army that I kind of actually enjoyed it. And I think I was quite fit from biking a lot and racing BMX and downhill mountain biking. And that just kind of gave me a bit of power. And then I could just run okay, not super fast, but I could just keep running for a long way. Okay. Hello to Leonard LDV. Great to have people like you in the chat. Should it not be decimal places, not significant figures? Tojabu Gaming. It could be 3 significant figures because that's our raw data here, or we could just keep it to 1 decimal place. It doesn't really. I mean, both of these are true, but basically what we tend to do is display all of our data in a table to the same number of decimal places. Am I doing a specific exam board? No, I'm trying to make this generic. I mean, most people, this question here, that can be used by anybody. These questions here, this is just general GCSE stuff. And when I do the live stream later on for A-level, I try and keep it generic because there are so many people doing different exam boards. If you want to see a specific live stream for AQA, EdXL or OCRA, I did some over half term, so you can catch those up. They're about 3 hours long if you want to go in there and kind of sort of see my kind of summary of the whole topic. Okay, that one there is all good. The professional carrying out the calibration claims that the percentage of X-rays absorbed is directly proportional to the thickness of the absorbing material. So when we have something which is directly proportional, if we were to plot the data on a graph, we would have a straight line that goes through the origin, and that would mean the two things are directly proportional. However, if we look here, we can see that if we double the thickness from like 1.5 to 3, the average was 13.7, and now the average is 24.1. So it hasn't doubled. We haven't doubled this to make this value double. If it really was a directly proportional relationship, we'd find that would go from sort of 13.7 to 27.4, which it didn't. So I would say probably if you were to plot this data, you wouldn't get a line like this. Instead, you might get a line like this. So state whether they are correct is your first point. The answer is no. And then you've got to explain that. So if you double the thickness, the energy absorbed does not double. And then, of course, what it's also good to do is give an example. And if you've been given a table of data, it's really important to maybe quote some numbers. So you could quote the values that it's given there. And that kind of justifies why you can actually come to that conclusion. Okay, sorry, Leonard, nice to see you. Thanks for being in the chat. You're working in an international school, so it's currently 1:53. So get to bed, that's too late to be up. But yeah, great to have you here. And it's great to have everybody from all around the world. I know there's a lot of people watching in the UK and England in particular, but I know there's always people from different parts of the world watching, which is always fantastic to be able to kind of share the physics. And a lot of the physics is identical no matter where you are. So it's great to have everybody there. Okay, then the next question is about the advantages and disadvantages of X-rays to ultrasound. So you've got to remember that an X-ray is a part of the EM spectrum, and it's an electromagnetic wave. Ultrasound is a high-frequency sound wave, okay? And that means it's a longitudinal wave, it's not ionizing, and so these two things both have advantages and disadvantages. So, for example, you could quickly check for a broken bone with an X-ray, but it's ionizing radiation and it damages human cells, so the exposure must be controlled. So if you've ever broken something or been to hospital or a minor accident unit, they might do a quick X-ray, and the people taking the X-ray, they stand out of the room, and that means they're shielded from the exposure. Ultrasound, though, is a high-frequency sound wave, so it's safe for internal imaging. So, for example, it could be used during pregnancy. You might have a scan when you go to the opticians, and they do what they call a B scan, where they basically use a little ultrasonic kind of thing that goes through your eye. It reflects off the different parts of your retina, and it kind of tells about the health of your eye. So things like ultrasound can be used for things where maybe X-rays aren't as suitable. Of course, ultrasound might be great for looking at some things, especially soft tissue, but it's not very good for actually checking for broken bones, and that's why X-rays are used for that. And I think that is the last question. If you want to find your own copy of these questions, go to my shop and you can download this, and that helps support this live stream. So if you listen to any of my live streams for many hours, I think I've done about 37 hours of live streams this exam season. If anything there has been useful to get you a couple of extra marks, then of course you can support me by buying more paper twos in my physics shop, and that is at physicsonline.shop. Okay, actually, I'm going to put that in the stream. At the moment, we've had, let's see how many people, of the 152 people who voted, 50 people pretty confident. I guess you've been watching my videos. The other 100, maybe not so confident and maybe not quite ready. What I'm just going to do in the chat is put in my online shop, which is physicsonline.shop. And if you go there, hopefully that means you can buy some stuff. Right, do we want the Lego? Yeah, let's do that. So we've got a brief interlude before I start A-level in about 2 minutes' time. This is the set of Lego that we've been doing, the kind of space set. And this is kind of how we've got so far. So I actually put them on a big board today. So this is kind of like the people or the robots and the aliens that we have here. My favourite one, I think, now is this one over here. This is Orion. I kind of showed it last night. So we've got Orion from Orion's belt. I also like this one here. That's definitely pretty cool. And I say that this is one of my favourite ones as well. So I'm sure these will pop up in some future videos. Hello, Matthew. Yes, it is time for Lego. I am a grown-up. This is my job. This is how I earn my living. So, yeah, you never know where like doing physics at A-level might take you. So we're going to look at some more Lego. Let me just zoom out a bit. So let's see what we've got. So I just open it. There we go. Right. Yes, here we are. So, okay, this one here has actually got 2 Lego figures in it. This is so strange, but okay, right. Actually, that's quite cool. So we've got this thing here, which is the pink Lego Space Baby. That's pretty cool, isn't it? Right, and then we've got, I guess the kind of, is it a robot or is it just a thing with a white face? That's quite cool. You can actually have it look like a robot. Let's do that one. So we've got, I guess, the kind of the mother of that baby, or like a robot that looks after them, and we've also got like a bottle of, I guess, space milk. Okay, that's pretty cool, isn't it? And can they hold? They can hold the baby. So there we go. Actually, I reckon, let's just turn it around and have that face there. So there we go. We have now completed the set. That's what's going on, Bilal. Hello, everybody who's just joined in for the A-level stuff. So we now have, I think this is probably the first ever series of Lego I've actually completed. So there we go. That is the Lego minifigures. Thanks to everybody, by the way, who has in previous streams donated a few pounds here and there. All of that money has been invested into this, plus all of the other bits of Lego that I got as duplicates and things. So I've got quite a few duplicate bits of Lego, which I'll do something with, I'm sure. So yeah, thank you to everybody who's donated, people who've got access to their parents' credit cards. Really, really useful because you can donate in the chat and do like super chats. Okay, people are saying... Right, people are saying they're cooked for paper 2. Everybody's using the word cooked this year. It must be the most used word in my live stream when I ask how people are going. Yeah, somebody messed up history paper 1. Miss Raff, don't worry about it. It's happened, it's gone, it's history now. All you can do is just think about the other kind of papers coming up. So if you didn't do so well in an exam, like if you found that OCR paper 1 for A-level was difficult, yeah. And people talking about some hard circles questions. Okay, right. So let me just zoom out a bit. So we're going to be doing some questions. Again, I said yesterday that I can't show AQA material. I'm going to be using OCR material, but this is going to be suitable for most people. Like 90% of the questions are going to be most suitable. If there's a question that you don't recognise, don't worry about it. Now, this one is a 2020 paper. Tomorrow, I'm going to be doing a bit more of a live stream where I'm going to go over 2018 and 2019. I'm sure you've done the questions, but again, it's just useful to look at the kind of, I suppose, my approach to things like this. So, right, this first question is OCRA only. So if you're an OCRA student, you should know about all of these. Barium, that is something which can, because of its really kind of dense kind of nucleus, that can kind of stop a lot of X-rays. So that's used maybe if you want to X-ray some kind of soft tissue. CAT scan, computerized axial tomography. Again, that's using like X-rays, kind of spinning around in a circle. Positron emission tomography. That is something where you're given maybe some fluorine-18, beta particles interact with the electrons and then emit some gamma. And of course, ultrasound is when we're using blood sonography to look at the speed of blood flow in arteries. And if you point the sensor, either you can see if blood's flowing away or to it. So D from EM, GM Galtz, Jack, Kai, Arman, Bramble, Octazuka. Yeah, this isn't GCSE, I'm afraid now. GCSE finished at 8 o'clock. We're now into the big stuff. So 8 p.m, we're going to do some A-level. So the answer here is D. Okay, which sequence shows the materials arranged in the order of increasing number, density of charge carriers? So basically, the number of charge carriers in an insulator is going to be quite small. The value of N is going to be big if you've got a conductor. And of course, if you've got something which is a semiconductor, that's going to have N, which can sort of change between these two values. So the order would be insulator first, which I guess it can't be this or this or this. So the answer for 2 is C. Excellent stuff, Jacob. Turtle Oaks. Yeah, lots of people there saying it's C. Jack Bernard. Yeah, is this question for AQA? No. I reckon this is more of an OCRA one, because it's an OCRA. You look at the number of charge carriers, which lets you look at the drift velocity of electrons. Okay, this one here, probably a bit of revision as well. I guess if you are doing AQA, but obviously you do know it. And this is OCRB at the moment. Do you need to know the numbers for the charge carriers? No, you don't. No. EdXL, sometimes they've let me show stuff, but I know some other teachers got copyright strikes for showing EdXL papers, so that's something I'm not doing on YouTube anymore at the moment. Okay, so we've got EM radiation, incident on the metal, we've got the work function, so that's phi. I'm not going to look at the numbers. You lot can, so you can kind of work out what the answer is. But basically, if it's something like this, ignore the fact it's multiple choice, treat it as a normal physics problem, and just do the maths normally. We've got the maximum kinetic energy of the photoelectrons is 1.7 electron volts. Okay, the frequency of this incident EM radiation is kept the same, but its intensity is doubled. What is the maximum kinetic energy of the electrons now? So we know that the energy of an incident photon is going to be equal to the work function plus Ke max. Now, if you were to keep the frequency the same, then the energy, which is equal to HF, is equal to the same. And that means each photon that lands will have exactly the same amount of energy. So each photoelectron will have the same kinetic energy. But if you double the intensity, we'd double the size of that current, the photoelectric current which is being emitted. So this must stay the same, which is 1.7, and therefore the answer is A. Well done, everybody. So Turtle Oaks, Bilal, Bramble, CM Galtz. Yeah, so exactly. Intensity does not affect the maximum kinetic energy. Right. Okay. By the way, people asking about solutions, I suppose one way around it is in the future for Year 12s who might be watching, the keen Year 12s who are still watching this, I might try and do more stuff on my website that isn't actually published on YouTube. That might be a way of getting around some of that copyright restriction, or even doing like more kind of Zoom tutorials. Okay, so we've got a big question. If I saw this in multiple choice, I'd leave it and come to it at the end because it's like quite text heavy. So a student is doing an experiment on the magnetic force experienced by a current carrying conductor in a uniform field. We've got the current, the length, the angle, the force. Okay, so what would be the correct heading for B? So if we're looking at B, then the unit of magnetic flux density is going to be Tesla. Okay, so it could be this, it could be this. We don't use the Weber, the Weber. That tends to be what we use for flux, magnetic flux. You know, the total amount of flux caused by the magnetic field strength times the area. The value for B, I guess we need to use F equals BIL cos theta. So B is going to be F over IL cos theta. And then it's a case of putting in the numbers. So we've got a force, 7.7 times 10 to the minus 2, divided by the current of 2, multiplied by the length, 0.12 times cos 30. Is cos 30 a half? I think it might be. I tried to remember it last night. Cos 30, it's not. No, sine 30 is a half, isn't it? Doesn't matter. It's all on the calculator. And this gives an answer equal to 0.37. So the answer is this one over here. So the answer is A. Okay. Square root of 3 over 2. Yeah, I should know that. Yeah. Okay, I need to get better at remembering like cos 30. It's like so basic. Like all of you know this, but it's just something that I just haven't done for so long in terms of actually having to remember it. We don't get that formula in AQA. Yeah, in AQA, I think you just get F equals BIL. Okay, but this here is basically this in AQA. It's kind of like everything's assumed to be at 90 degrees, but effectively what we can say is that one of these may be the length of wire, and therefore I guess the I guess it's just basically saying that this here isn't perpendicular, it's at an angle. We just want to find the component of that that's perpendicular to that. F equals BIL sine theta. Oh, hold on. It is. Have I done it wrong? Do you know what? Oh, yeah. Yeah, I think it is sine theta. So, have I done that? Let me just see what the data book says. Have I just used the wrong term? So here we're looking at where is it? BIL sine theta. Okay, ignore me. I wrote down the wrong thing because I was reading comments and I just got it messed up. So yeah, it says sine theta. That's what the data book says. I don't know why I put cos. I think it's because with AQA you have like BAN cos theta. So 0.5. So 0.64. So the answer, if you've just tuned in, this is just me messing it up. There we go. The answer is B. Yeah, because it's on the perpendicular. Okay, so the answer for 4 is B. Not doing so well there. Right, I'm going to concentrate on this. The diagram shows the oscilloscope trace for an electrical signal. The time base is 2 microseconds per centimetre. What's the frequency? So I would say that the time for one wave cycle is equal to 4 centimetres, and we're going to multiply that by 2 microseconds. And of course the frequency is 1 over the time period, so that's 1 divided by 4 times 2 times 10 to the minus 6. So that's 1 divided by 8 times 10 to the minus 6, which is 125000. So that's 125 kilohertz. Again, something like this. This is just a simple calculation, hopefully. I got this one correct. And therefore, I would say don't look at these just because they're the kind of things that can kind of confuse you very slightly. What's the difference between a signal generator and an oscilloscope? So basically, the signal generator will generate the signal. The oscilloscope is what measures the signal that's inputted into it. So yeah, so basically this can take any signal, it just tells you what the signal is, but this will have been generated often by a signal generator. There will be a stream tomorrow, failed organ. Yeah, there will be that at 7:30 till 8 for GCSE, and it might go from 8 till 9 potentially for A-level, just because there's maybe a lot of stuff that people might be asking. Okay, progressive and stationary waves. What's correct? A progressive wave has at least one node. Note, because you only get nodes in stationary and standing waves. All progressive waves are longitudinal. That's not true because transverse waves are progressive as well. All particles oscillating between two adjacent nodes in a stationary wave are in phase. Yes, that's right. So basically, if you've got like a standing wave like this, and maybe a small amount of time later it looks a bit like that, okay? Effectively, all of these bits go up at the same time, and all of these bits go down at the same time. So if we look at maybe the distance between a node and an antinode, all of these things all move up at the same time, and they all move down at the same time. So all of these particles between two adjacent nodes are in phase. And of course, two waves travelling in the same direction produces a stationary wave. That's not true. They have to travel in the opposite direction. So the answer for 6 is C. Yeah. For the area under the graph, what is the most optimal way to find it? Good question, Rish. Basically, I would say if you've got something like this, try and avoid counting squares. Instead, I would say you want to approximate it maybe as a triangle. And if you know the triangle, it's just half base times height. So effectively, the best way to do it is maybe to kind of think about drawing triangles, which maybe have bits which kind of go over it, bits which go under it, obviously with your ruler. Okay, and I think you can basically break up the shape of a graph into smaller shapes, which is easier to find the area of, okay, rather than counting squares. Okay, right, we now have a capacitor. All of you should love this. So we've got the power supply has an EMF of 10 volts, negligible internal resistance, C and R. The switch is closed at time t equals 0. We've now got the potential difference across a resistor at various times. So what is the product C times R for this circuit? So basically, what is our time constant? Okay, so for this, basically, there is an equation that all of you are given. So I'm just going to see what the comments say. Right, capacitors will be the death of you. Yep. Yeah, trapeziums, Kyle. Trapeziums work for the area under shapes as well. I just think take the area under a line, rather than counting squares, just make it into like triangles, trapeziums, rectangles, work out those individual areas and add them together, and that's the quickest way to do an approximation of the area. Okay, so the time constant. Now, there is an equation to do with this, with capacitors, where it basically says a time constant is equal to RC, okay? And that time constant is the time for it to discharge to 1 over, well, basically for 63% of its energy to be lost, okay? Now, what's the best way to show this? I guess because looking at this, if it's gone from 10 down to 3.7, that's basically a 63% reduction. And that means that value there, 6 seconds, is going to be the correct answer. So the answer is D. Now, the way to maybe show that, yeah, so it's 37% of its initial value. So let's have a look. I suppose another thing you could say is that if this is, if we want to look at the potential difference over time, we could say that V is equal to V naught e to the minus t over RC. And basically when RC is equal to the time constant, that's when it's going to go down to 37% of its original value. So what you can do is look at, what's the best way of doing this? Yeah. Okay. Right. So, I would say that for this one here, yeah, basically, so I would say that the half-life of this is going to be equal to 0.2 RC, and we know that the time it takes to half to go from 10 to 5 is going to be equal to 4.2 seconds. Okay, so if you do 4.2 seconds, divide that by the natural log of 2, that gives a value equal to 6.05, which means 6.0 seconds is going to be the time constant for that circuit. Yeah, is that all good? Sorry, that's not explained very well. I probably should have looked at these questions before I did them tonight. Okay, right, a capacitor discharges through a resistor. At time t equals 0, the PD is that. At time t equals 2, v equals 0.9. Which statement is not correct? Okay, so basically in 2 seconds it goes down by 10%. So it's 90% of its original value. So from 0 to 2 it goes down from whatever 1 to 0.9, and if it goes down by another 0.9 after 2 more seconds, that's going to be equal to 0.81. So that one's correct. The capacitor is fully discharged after 10 seconds. That's not correct, because we have this exponential thing where it kind of gets closer to being fully discharged but not quite getting there. That graph isn't good, is it? So we don't quite get to 0. The PD across a resistor is the same as that for the capacitor. Yeah, because what we have is basically whatever the PD across that is going to be the same as the PD across that. That might be plus, that might be negative, but basically there's no, the PD there plus that is equal to 0. And the potential difference V decreases exponentially with time. Again, that's going to be true. So we have this exponential decrease. And so the incorrect statement is going to be B. Okay. Yeah. Right. Yeah, never touches 0. Cool. Yeah, I see everybody, when I make a mistake, this is the thing, it's like, it's not hard physics, but it's hard physics trying to explain it in a live stream. If you make a mistake, by the time I realise, everybody else on the chat has already jumped in. So it's really good that so many people there are kind of seeing where I'm making errors and actually trying to make it as clear as possible. Okay, right. Okay, another one. So for this, what's the value of n at time t equals 30? So what I would do for this, the quickest way is basically saying 2000 divided by 1900, or 1900 divided by 2000 is equal to 0.95. So basically what we've done is we multiplied this number by 0.95 to get this number. And then we just need to multiply this number by 0.95 to get 1805, times that by 0.95 to get 1714.75, which looks to me like the answer is C. Okay, is that right? Do let me know. Yeah, so basically there's an equation that looks at how dn, or delta n by delta t, is going to be equal to minus 0.5 n. You could of course just say that delta n is going to be equal to minus 0.5 times delta t times n, and that's going to be 0.5 times 0.10, which is just 0.05. Okay, which is why we're multiplying this by 0.95 each time. Okay, but I would say, yeah, a bit like compound interest, as Memford said there in the chat. Basically, it's just you're multiplying each number by this each time, and that's quite a quick question, isn't it? Okay, the total energy released in a single fusion reaction is 4 mega electron volts. What's the change in mass? So delta E equals delta mc squared. So the change in mass is going to be equal to the change in energy, which is 4.0 times 10 to the 6 times 1.6 times 10 to the minus 19. So that's to go from mega electron volts into joules. We're going to divide that by the speed of light squared, which is 9 times 10 to the 16. Okay, so yeah, how's it all looking? Right, so 4 times 4 times 10 to the 6 times 1.6 times 10 to the minus 19 divided by 9 times 10 to the 16 is equal to 7.11 times 10 to the minus 30. So I would say the answer for this is going to be B. Okay, I do think sometimes that this is a useful thing to remember, knowing that this is just equal to 3 times 10 to the 8 squared. So that just saves me a bit of time in my writing that out. How are people doing? How are people feeling? Let's have a look at what the poll says. Are people more happy? Again, we've got about 300 people. If you haven't voted already in the poll, just do a quick vote. Are you ready for Physics Paper 2? Are you one of the 35%, the 100 people ready for it and kind of just can't wait till it happens? Or are you one of the massive 64% now who are maybe not ready? So do let me know in the poll. And of course, if you haven't already done so, do like the stream. Click on the heart or the 100 or the faces. I don't really know what that does, but I think YouTube likes it. Yeah. Right, 11. A stationary sound wave in its fundamental mode of vibration is formed in a tube open at both ends. So if it's open at both ends, immediately I just put an antinode at each end. There must be a node in the middle if it's the fundamental mode of vibration. And then I just kind of sketch what it looks like. So it looks a bit like this. Okay, the length of the tube is 0.17, the speed of sound. Which row for this stationary wave is correct? So the number of nodes, we'd have an antinode at each end. There'd be one node, so it must be A or B. Now the frequency is going to be equal to the wave speed divided by the wavelength. And here, the length of that tube is equal to half the wavelength. So the velocity is 340. The wavelength is going to be equal to 2L. So that's 2 times 0.17, which is 340 over 0.34. Now, of course, you can always do that in your head, but I find when you do stuff like this, it's easy to like make a power of 10 error. And that means the frequency is equal to 1,000, which is this one over here. So the answer is B. Okay, right. B says Bilal, Junaid, Armin, yes, B, correct answer, well done. Bramble, B as well, fantastic stuff. Okay, the table below shows the quark composition of 4 particles A, B, C and D. Which particle has a positive charge? I would say, looking at this, the answer is A, just immediately. Okay, does everybody know the charges on different quarks? You should know, especially if you're AQA, you did this loads in year 12, and if you're OCI, you'll have done it before. You should know that that is the quark composition for a proton, up, up, down. A neutron is up, down, down. I can't remember what these are. Doesn't matter, but we know a proton is positive, and therefore the particle A must have a positive charge. And that question is the kind of thing that, you know, you want to be doing that at the start of the exam to kind of help build your confidence. Okay, the next question. Oh, I hate these ones. This is probably my least favourite area of A-level physics to explain, looking at the size of the field. Okay, so we've got the electric potential at a distance r from the centre of a charge q is 40 volts. Okay, so we know that here, effectively V is going to be equal to Q over R times 1 over 4 pi epsilon naught. Okay, so I've just done something weird with my chat. Right, there we go. Yeah, so, sorry. So I'm just seeing what the chat says. Yeah, you do get a table in the equation book with charges for quarks, Tommy, but you just remember that. You should just recognise that an up, up, down is a proton, hopefully. So yeah, S is strange. Some of this might be paper 1 if you are maybe AQA or something, but this is basically just most of your questions. However, everybody has this. Okay, and also, yeah, that's something that Customize MC, that's completely true. Paper 2 could still legitimately ask about anything in paper 1. I don't think they would ask a big question about it, but the assumption is if you're doing paper 2, then you've already done paper 1, so you know everything about that. Okay. What is the potential at point P for the arrangement of charges Q and minus 1.5 Q as shown below? So here we've got the same distance, and what we need to do is basically say the potential at point P is going to be equal to the potential due to this charge over here, which is equal to 40, which is what it has up here. Okay. We also have something which is the same distance apart, but it's going to have a negative charge. And if we know that effectively looking up here, we can see that V is proportional to Q, then the charge here, well, if 40 is proportional to Q, if you've got minus 1.5 Q, that's going to then be proportional to minus 60. So you've got 40 plus minus 60, and here that potential is equal to minus 20. So I say here the answer for 13 is A, which is what Ben says. Yeah, I think this is a difficult one. I hate this bit of physics. It's so difficult to explain without kind of tying yourself in knots. Okay, hopefully that helps. Right. The potential difference across the lamp is 2.5 volts. The current is 20 milliamps. What is the energy dissipated in a time of 3 hours? So the energy transferred is equal to ITV, which equals 20 times 10 to the minus 3 times 3 times 60 times 60 times 2.5. I'm sure we had a very similar question yesterday, didn't we? I get this to be 540, and therefore I think the answer for this is just D. So again, although it's a multiple choice thing, basically this is just a case of just some simple physics. Junaid, yes, great stuff, getting D as a right answer. Okay, right. The last question we'll do tonight as part of this, almost exactly to half 8 it. What can be deduced from the diffraction of electrons by a thin film of graphite? So, everybody in the chat, all of you know this, don't you? You've done some quantum stuff, probably came up in paper 1. So what can be deduced from the diffraction of electrons by a thin film of graphite? People are saying B. What do you reckon? D, says Tommy. D, says Junaid. Is that Lieutenant Turtle? We've got another Turtle Oaks. There's a lot of turtles here tonight. Evidence, B. Meme Lord, D. Ben, D. We've got Ibtisam saying D. Joel, D. Mr. Cow, D. 78J says D. GM Galtz, Scarface, Sam, Silver Crow, Routine Client, Bilal, Boat, all of you saying D. Yeah. So that's a true statement. That's a true statement. That's a true statement. And that's a true statement. They're all true. But what do we know about the diffraction of electrons? Well, if they're diffracted, it means they must be travelling as a wave. So there we go. That thing there is what we see. Does electron diffraction form a stationary wave? No, we basically just get interference between them where effectively the wave cancels out in parts, which is where you see the kind of the darker fringe, often like a circular fringe, and then some of the electrons, if there's 2 electrons in one place, they kind of add. So it's like the wave-like properties that we see. What pen is this? This is a V-Sign pen. This is actually a new one tonight because the one I had yesterday ran out. So far, I've been doing lots of live streams. My red one is almost empty. The black one you can see is almost empty. The purple and other colours are pretty good. So these will go for a bit longer. Okay. What did I say to focus on, John? Good question. There are so many things you could be working on. I would say the main thing isn't so much the content, it's about just the way that you approach the exam with like a good kind of mental attitude of knowing that there will be some tough questions, but you just got to leave them till the end and get lots and lots of the easy marks, and just really carefully, before you rush into answering it, really read the question and actually work out what they're asking for. Okay, so GM Galt says, you do get confused when you answer the question, okay? If you're good with learning the content, yeah, I think that's a perfectly normal thing. I'd say that most people now are in a similar position where most people have the same amount of knowledge, and what's going to kind of set you apart from other people is how you apply that in the exam. And I think the best thing to do, because you've got plenty of time, is just to maybe do as many past paper questions. You don't even need to write stuff down. So even if you're just reading through a paper, it's going to kind of show you the kind of questions which might come up. You might just do some rough working out. You don't need to be writing full long sentences. You just need to be just looking at the kind of style of questions, looking at the mark scheme, and that's going to really kind of give you, in the next 24 hours or 48 hours, probably 24 hours is what you need. That's going to give you just so many different past papers that you've been experienced with. Yeah. So, do I have videos on the things that you need to know? I reckon I've got about over 1,000 videos somewhere all over the place. But if there's anything that you're not sure about, definitely go and have a look at A-level physics online. There's loads of videos there that can help just remind you of everything you've covered already. So yeah, apart from that, I'm going to be back again tomorrow. I'm going to probably do a longer live stream if anybody else wants to join me. We'll just, again, do some more similar questions. Hopefully not kind of scare you too much, because basically if you can't do it by tomorrow night, you're probably not going to learn it if it's a big, new, complicated area. So we'll just do some questions on a variety of topics. Ideal for OCR because they're the papers I'm using, but still useful for Edexcel, OCRB, AQA, WJC, CIE, Educast. Anybody doing exams? Anybody doing Educast here? I don't know, but yeah, basically that is the plan. And I've got no idea, I'm afraid, Boat 7, about what the grade boundaries are. I think it really depends upon just how everybody gets on. Hopefully I can do my part to raise the grade boundaries. But yeah, thank you everybody in the chat. I'm reading all of these. Yeah. I probably won't be doing routine client live streams in September because everybody has mocks at different times. But I will be doing a lot more stuff over the year, especially as I have a big new studio that's kind of coming together. So yeah, good night everybody, and I'll see all of you tomorrow.